Welcome all. Today we will discuss about design strength of tension members. You can refer to clause 6.1 page number 32 of IS 800 2007. Here it is the smaller of the following two limit states: limit state of yielding in gross section and limit state of fracture or rupture in net section. Another limit states also comes into play, that is the block shear. Now coming to gross section yielding. When a tension member is subjected to tensile force, the deformation within the length of connection will be smaller than the deformation in the remainder of the tension member. It is because net section exists within a small length and total elongation is the product of length of the member into strain attainment of yield stress on the gross area will result in larger total elongation due to unreduced cross section. This makes one of the limit states of strength corresponding to the yielding of gross section. The load on gross section must be small so that stress in cross section is less than yield stress Fy. Load T by Ag should be less than Fy. T should be less than Ag into Fy. Ag is the gross cross sectional area and Fy is the yield stress and T is the load. The formula can be referred from clause 6.2 page number 32 of IS 800 2007. Here it is given that design strength TDG is equal to T by gamma m0 is equal to from the above equation we got Ag into Fy by gamma m0, where TDG is equal to design strength and gamma m0 equal to partial safety factor 1.1, referred from page 30 table 5. Now coming to net section rupture. A tension member is connected to other members or gusset plate by bolts or welds. The bolt holes reduce the cross-sectional area. Here the bolt hole will reduce the B, which is referred to as net area of the member. At service loads, these holes cause stress concentration adjacent to bolt holes. Here the stress concentration has become Fy. Now on increasing the load, the redistribution of stress takes place and additional stress is transferred to adjacent areas. Here additional stresses will transfer to the adjacent area of cross section. Stress in the fibers adjacent to holes remain constant, that is Fy, and the fibers away from the hole progressively reach the yield stress Fy. So here we get the expression T is less than An Fu. An is the net area. So Tdn is equal to T by gamma m1 is equal to An Fu by gamma m1, or Tdn equal to 0.9 into An Fu by gamma m1 can refer clause 6.3.1 page number 32. For welding and bolted connection of single angles, Tdn can be written as 0.9 ANC Fu plus by gamma m1 plus beta Ag0 Fy by gamma m0. Refer clause 6.3.3 page 33, where beta is given by 1.4 minus 0.076 into W by T into Fy by Fu into Bs by Lc should be less than equal to Fu by Fy into gamma m0 by gamma m1 should be greater than equal to 0.7, where W and Bs are indicated in the figure also given in code book IS 800 2007. For bolted connection, Bs will be equal to W plus W1 minus T, and for welded connection, Bs will be equal to W. In the expression, T is the thickness of the angle leg, Lc is the length of the end connection, An equal to net area of total cross section, Anc equal to net area of the connected leg, Ag0 equal to gross area of the outstanding leg, gamma m0 equal to 1.1 and gamma m1 equal to 1.25. Table 5, page 30 of IS 800. Now let us come to a question. Compute the tensile strength of an angle section ISA 150 into 115 into 8 mm of Fe410 grade of steel connected with the gusset plate as shown in figure for following cases. First one is for gross section yielding and next is for net section rupture. So here you can see that ISA 150 into 115 into 8 mm is connected to a gusset plate with welded connection. Now the length of weld at the end connection is 140 mm. Here it is given Fe400. So for Fe400, Fu will be 410 Newton per mm square and Fy equal to 250 Newton per mm square. Gamma m0 and gamma m1 will be equal to 1.1 and 1.25 respectively. A0 means gross area of ISA 150 into 115 into 8 mm will be equal to 2058 mm square, which can be found out from the steel table for unequal angles. Now first coming to tensile strength due to gross section yielding. We know TDG equal to AgFy by gamma m0 is equal to Ag, here we have got 2058 mm square into Fy is 250 by 1.1, which gives 467700 Newton is equal to 467.7 kilonewton. So tensile strength due to gross section yielding is equal to 467.7 kilonewton. Now tensile strength due to net section rupture. Here longer leg is welded or connected to gusset plate, that is 150 mm leg. Next the short leg is outstanding leg, so Bs will be equal to W will be equal to 115 mm. Now weld length along the direction of load LC will be equal to 140 mm. So we know beta is equal to 1.4 minus 0.076 W by T into Fy by Fu into Bs by Lc. This should be less than Fu by Fy into gamma m0 by gamma m1. This should be greater than 0.7. Now beta will be equal to 1.4 minus 0.076 into W is equal to 115 by thickness of angle is 8 into Fy 250 into Fu by Fu 410 into Bs is equal to 115 divided by Lc is equal to 140. So the value of this expression is equal to 0.85. Again, Fu by Fy into gamma m0 by gamma m1 is equal to 410 by 250 into 1.1 by 1.25, which gives 1.44. So relating them, we got value of beta equal to 0.85, which is less than equal to 1.44, and it's greater than equal to 0.7. So the value of beta is 0.85. Now net area of connected leg A and C is equal to 150 minus thickness by 2, 8 by 2 whole into thickness is equal to 1168 mm square. Gross area of outstanding leg AG0 is equal to 115 minus thickness by 2 whole into thickness is equal to 888 mm square. So TDN will be equal to 0.9 ANC Fu by gamma m1 plus beta Ag0 Fy by gamma m0 will be equal to 0.9 into 1168. Here we have calculated ANC into Fu is 410 by 1.25 plus 0.85 into, here we have calculated AG0 equal to 888 into Fy we know 250 by gamma m0 we know 1.1. This gives the value 516340 Newton is equal to 516.34 kilonewton. So here we got both the values, that is tensile strength due to gross section yielding and tensile strength due to net section rupture. Now coming to block shear. This type of failure is characterized by tearing out of a segment or block of material at the ends of a member. For certain connection configurations, the block shear occurs only a path involving tension on one plane and shear on a perpendicular plane. So here this is the shear plane, this is the tension plane. Block shear strength is as follows for plates and angles. You can refer to clause 6.4 page 33. Here what happens, there are two planes, shear plane and tension plane. It may happen that first shear plane will fail, then tension plane will fail, or it may happen that first tension plane will fail and then shear plane will fail. According to that, there are two conditions. One is shear yielding and tension failure. Here tension plane will fail first and shear will yield. Second one is shear fracture and tension yielding. Here shear plane will fail first and tension will yield. So from this we got two formulas. T dB1 equal to AVG Fy by root 3 gamma m0 plus 0.9 ATN Fu by gamma m1 and T dB2 is equal to ATG Fy by gamma m0 plus 0.9 AVN Fu by gamma m1. So block shear strength will be minimum of the above two values. Now coming to a problem, determine the block shear strength of the tension member shown in figure. The steel is of grade Fe410. Here an angle section ISA 80 into 50 into 8 mm. This angle section is connected to this gusset plate. The bolt holes are of 18 mm diameter. Here the distance between this end and this bolt is 50 mm and these two bolts is 100 mm. The distance between this end and this bolt is 35 mm. Let us take this section to fail in block shear, that is A, B, C, D. Here you can see A, B, C, D. So here the length will be A to center of this bolt hole is 50 mm and center of this bolt hole to center of this bolt hole is 100 mm. Center of this bolt hole to this edge is 35 mm. Now for Fe410, Fu will be equal to 410 Newton per mm square and Fy will be equal to 250 Newton per mm square. And we know gamma m0 equal to 1.1 and gamma m1 equal to 1.25 from table 5 page 30. So here it is already been told the shaded area will shear out. Now AVG, gross area in shear, will be equal to 1 into 100 plus 50. 1 into 100 plus 50 into thickness of this angle section is 8 mm will be equal to 1200 mm square. AVN, it will be AVN, net area of shear will be equal to 1 into 100 plus 50 minus 2 number of bolts minus 2 minus here half of the bolt will be cancelled out minus half hole into diameter of bolt hole 18, total hole into thickness of the angle section 8 will be equal to 984 mm square. Again, gross area of tension region will be equal to this one, 35 into 8 is equal to 280 mm square, and net area of tension region will be equal to ATN is equal to 35 minus half into diameter of bolt hole into 8 will be equal to 208 mm square. So block shear strength will be minimum of TdV1 and TdV2. TdV1 we know AVG Fy by root 3 gamma m0 plus 0.9 ATN Fu by gamma m1. Putting the values we got to 18.86 kilonewton, and TdV2 is equal to ATG Fy by gamma m0 plus 0.9 ABN Fu by root 3 gamma m1 will give you 231.34 kilonewton. So minimum of these two is this one, 218.86 kilonewton, that is TdV1. Thank you.